Okay, so good afternoon, everyone. Welcome. So last time we proved the first of our properties of convergence for series. Yeah, we proved our linear combinations result, which said if you've got two convergent series, the series AM and a series BM, if they both converge, then when you form a new series, just shown at the bottom there, when you form a new series by taking linear combination, a fixed linear combination of the terms from the two series, that series is convergent. That series is convergent, and its limit is that same linear combination of the limits of the two series that you used. Okay, and we proved that using the definition of convergence for series. Okay, now we also glanced at these other two tests, which were the general term test on this page and the geometric series test. So these two tests are on page 14 of your notes. So I'd just like to take you through the arguments for these, the justifications of these, and then we'll look at some examples, make things a little bit more concrete, and look at a collection of examples which show applications of these two results, the general term test and the geometric series test, and also some other ideas that can be used in series convergence as well. Okay, so we have to prove the general term test. Now, it's got these two equivalent versions. So it comes into, you can state the test in two ways. You can either say, case one, that if the sequence of terms has a non-zero limit, so if the limit as m goes to infinity of am is not zero, the conclusion you can draw from that is that the series is divergent. Okay, because if the step size isn't shrinking to nothing, if the step size is settling down to some fixed non-zero limit, then the series isn't going to converge, because the series is just going to act like adding an infinite number of that limiting step value together, and that's going to diverge. Or another way of saying it, which the implication is going in the opposite direction, but it deals with a convergent series. If a series is convergent, so if the sum of AM converges, that tells you that the limit of the terms of that series must be zero. So the only way in order for a series to converge, it must be the case that the step size is shrinking and converging to zero. It doesn't say that that's enough to give convergence, because remember, we had the lovely example last time of the harmonic series. That was a series it's 1 plus a half plus a third plus a quarter and so on. The step size there was shrinking to nothing, was converging to zero, but yet it did so slowly enough so that the series still grew without any upper bound, okay? Because we produced an argument that showed that it was greater than an infinite sum of halves, and so it was unbounded. Okay, but let's see about proving this. So we're going to take statement 2. So we'll prove version 2. But the two versions are equivalent, and this same argument can be used to, if you just state it in the right way, can be used to prove version 1. So we have to prove that this statement, that the series converges, implies that the limit of the terms is zero. So we should assume that we've got a convergent series. Okay, so suppose the series, the sum of am from 1 to infinity converges to a limit L, say. Yeah, I think we're going to need to name the limit. We're going to need to talk about the limit. Now so that's the assumption we're making. And we want to prove that the limit of am is zero, as is the conclusion there. Now, what exactly does that assumption mean? Let's write down precisely what that statement means. So what does it mean for an infinite series to converge? what that means, so we can say that is the limit of the partial sums. So when you sum from 1 to k, that series there is a finite sum. That's the kth partial sum. And you take the limit of that as k goes to infinity, that means that is equal to L. Okay? That's what it means for our series to converge. Now we want to draw a conclusion about the behavior of the sequence terms A, An. We want to show that the limit of Am is equal to 0 as m goes to infinity. Now, what's a nice way? You see, we've got this statement about the partial sums, and we want to draw a conclusion about the behavior of the individual terms themselves. So we need a neat way or a convenient way to link the two ideas, link the partial sums to the individual terms. Okay. So notice that we can express the term we can express the term AK as, oops, sorry. Is there a convenient way we can write the term AK out of partial sums? Because my assumption tells me about the behavior of the sequence of partial sums. Is there a neat way that we can express the element AK? How can you assemble that or write that as a certain combination of partial sums? So there's a few gaps here. There's a gap is there's some operation here, and there's those two, there's the upper limit of each sum. So what fills in the gaps? You got 3 gaps there. Anybody want to? The individual single term AK, how does that relate to 2 of the partial sums? So if you can only work with the partial sums, how can you work with them in some way, some operation in here, so that the result that falls out is just the single element AK? We see neighboring partial, yeah, go ahead. Minus operate, yeah. So the difference between 2 certain partial sums. So which partial sums? Yeah, exactly. So the sequence element AK has this nice expression as the difference of 2 of the consecutive partial sums, just chosen carefully. So you take the kth partial sum and you subtract the k minus 1th, and that gives you the term AK. Now, normally that would be a pretty funny way of writing AK, because AK is just a single element, and here you're making it up out of a kind of confusing mixture of loads of other A's. You know, so normally you wouldn't bother writing something simple like AK in this complicated way. But the reason we do it is because we've made an assumption about how the partial sums behave. Right? I've made an assumption about the behavior of the sequence of partial sums. And the conclusion I'm trying to draw is about the behavior of the single sequence elements. But now I've got the sequence element as a combination of partial sums. And so I can use what I know about the partial sums to get me to the conclusion about the elements. Okay. So how do we do that? Well, so this is good. So we're going to use this. So what we need to show, in order to show that the limit of AM is 0, we need to show that given any epsilon, given any positive value epsilon, we can find a capital K such that for all values of the index little k larger than capital K, we have the absolute value of AK strictly less than epsilon. Okay, that is using the definition for convergence of sequences. So that's the definition of convergence for sequences. In order to show a sequence converges to 0, you have to show that given any radius epsilon, eventually the distance between the element and 0, or which is just the absolute value of the element, that distance is less than epsilon. So that's what I have to show, but I can use it using the similar behavior for the partial sums. So given epsilon bigger than 0, we know, now how will I have to choose this slightly carefully. Maybe a little sketch will help me clear up in my mind what I'm trying to do. So here's the limit L of the series. Yeah, if I make the radius epsilon over 2, if I make the lower limit of this interval be L minus epsilon over 2, the upper limit be L plus epsilon over 2, I know that after a certain point, all the partial sums belong in here. And so the difference between any two partial sums will be at most the radius of the interval. And the radius of the interval is epsilon, and that's what I need to make it less than. So, yeah, we know there exists a J. No, we'll say that we know there exists a K such that for all K bigger than or equal to capital K, let's write it like this. The absolute value, the partial sum, the kth partial sum will be an element of this interval here. So it'll be somewhere between L minus pi over 2 and L plus pi over 2. So after this point, capital K, all the partial sums are inside this interval. So therefore, the distance between any two of those partial sums, can be at most epsilon, okay? Because they're both inside this interval. So i.e., for all K greater than or equal to capital K, the difference between the sum to K minus the sum to K minus I'll have to make this K plus 1 to K this absolute value is less than epsilon. Okay, because for every little k bigger than or equal to capital K, these two partial sums have to both be inside this interval. And the difference between these two partial sums is the element AK plus 1. Okay, so that proves that theorem. So we started off with the assumption that if our series converges, and then we related the sequence element AK, we linked that to a certain combination of partial sums, specifically the difference between consecutive partial sums. And because we know this partial sums as a sequence converges to the limit L, we know that after a certain point, we contract those partial sums inside this interval here around L. Okay. So that means the distance between any two of them that are trapped inside this interval, it's at most epsilon. And so that means the absolute value of the sequence term, AK plus 1, is less than epsilon. So after a certain point, the sequence terms are all less than epsilon. And we can perform this given any value of epsilon whatsoever. So if we wait around long enough, the sequence terms get as small as we want. So that means they converge to 0. Okay. So we've shown that the limit as k goes to infinity of the sequence terms AK is equal to 0. So that's the proof of the general term test. And we'll see some applications of that in a moment. After we've looked at the proof of the geometric series test. Okay. So here's the geometric series test. So geometric series is one of this form up here. It's where the terms can be written as some combination A times R to some power n minus 1. So A is the initial term of the sequence of the series. So it's the series that looks A plus AR squared plus AR cubed, etc. Okay. Well, there's the trivial case we can deal with first of all. So this is the proof of the geometric series test. Well, if A is 0, then the series is just 0 plus 0 plus 0, and there's not much to say about that except that it's equal to 0. If you add an infinite amount of zeros together, you're never going to get anywhere. It's always just 0. So if A is 0, it's convergent. So that's just a trivial case to get out of the way straight away. So we assume A is not 0. So we've dealt with that. So now we want to prove that the series converges, and it depends on the absolute value of the common ratio R. So R is the multiplying factor which generates each term of the series from the previous one. The test is saying that the series converges if and only if R is strictly less than 1. So it converges if R is strictly less than 1, and it diverges otherwise. Okay. Now to prove this, we need a nice, we need to find a nice formula for SK, the kth partial sum. So what's a nice formula for SK? I think this was one of the tutorial exercises in the sequences chapter. Notice that SK, well, if we write it out like this, it's kind of easier. So you're adding all these things up got AR to the K minus 2, and then the last one is AR to the K minus 1. But we notice that if you multiply SK by R, that has the effect of shifting everything one step along the way. So if you multiply SK by R, what do you get? You get AR plus AR squared plus AR cubed. And the second last one is now AR to the K minus 1, and the very last one is AR to the K. Yeah. So SK and RSK are almost the same. They're almost the same. So when we subtract them, we will get almost 0, not quite. So not exactly the same, but they're almost the same. So everything cancels out, you notice. AR cubed will cancel with the AR cubed, which is sitting there. AR to the K minus 2 cancels with the AR to the K minus 2, which is sitting here. And the K minus 1 cancels with that. So all of the terms cancel out except the top left one here and the bottom right one here. So you're just left with the A on top minus the AR to the K there. Now that expression is nice because it features the kth partial sum SK, but it no longer has this dot, dot, dot in the middle of it. It just expresses SK really as, you know, a definite sum of two terms. Now this can be quickly reorganized to give this kind of a formula. For SK. So that's the kth partial sum of a geometric series. And that's for any geometric series. Any geometric series as long as R isn't equal to 1. If R is if R is equal to 1, then really the geometric series is just A plus A plus A plus A plus A. And there's no question. If A is non-zero, then it will definitely diverge. So you need to exclude R equals 1 because, of course, you can't divide both sides by 0, of course. Anyhow, so this is our nice formula here. And it's very easy to work out what the limit of that is. Remember, we're trying to find the sum of the series. So if the absolute value of R is less than 1, notice that R to the K converges to 0 as K goes to infinity. So if R is a number strictly between -1 and +1, as you take successive powers, the number shrinks. Okay, because you're rescaling it closer to 0 each time. So you're multiplying it by another number R, which is less than 1. And if the absolute value of R is well, we've already excluded, let's say if it's greater than 1, strictly greater than 1 or equal to -1, then R to the K is divergent. It's a divergent sequence. If R is -1, R to the K is just going to go -1 + 1, -1 + 1, -1 + 1. It'll be divergent. And if it has absolute values strictly bigger than 1, then when you take successive powers of it, R to the K, as the K goes to infinity, R to the K is just going to grow without any upper bound. Okay. So having noticed that, that's how K appears in this formula. So that allows us to understand what happens to SK as K gets larger. So if the absolute value of R is strictly less than 1, then the limit as K goes to infinity of SK Well, because this bit goes to 0, that means you're just left with a over 1 minus r. Now we're using there the algebra of limits theorem for sequences. Okay, because in order to break apart this limit here as the sum of the limits of its constituent parts, we need to use the algebra of limits theorem for sequences to break down this complicated expression down into the combination of the individual limits. And because the RK is converging to 0, that's going to disappear effectively, and you're just left with a over 1 minus r. Okay, so that's exactly the result there. We want the sum of the infinite series to be a over 1 minus r. Because remember, the limit of the sequence of partial sums, that's exactly what we mean by the sum of the infinite series. I.e., the sum of the infinite series from n equals 1 to infinity of ar to the n minus 1, that's equal to a over 1 minus r. And if this r is strictly bigger than 1, then this thing is going to be divergent, so the SKs are going to be divergent, and so the infinite geometric series is divergent. Okay. So, okay, any questions or queries about that, or things you'd like me to clarify or say some more about there? Okay, let's look at a few examples now. So let's do a quick application of the geometric series result. Yeah, so we'll look at 1 over 5 plus 1 over 5 squared plus 1 over 5 cubed, 1 over 5, 4, this series. Does this series converge? Well, the first thing to do is to recognize that as an example of a geometric series. Each term is just a fifth of the previous term. Okay, so yeah, it is a geometric series. So this is the geometric series sum of AR to the n minus 1. And you've got the initial term is a fifth, and the common ratio is a fifth as well. And notice that the R has absolute value less than 1. It's a fifth. So it will be convergent according to the geometric series test, and it will have the limit a over 1 minus r. So this is convergent, we can say, as the absolute value of a fifth is, of course, strictly less than 1, the absolute value of r. So adding up well, really we're adding up a fifth to the power n. Adding up all the powers of a fifth gives us a over 1 minus r. So it's a fifth over 1 minus a fifth, which is, what is it? It's a fifth over 4 fifths. So what's that? A quarter. Okay. So it's an example of seeing a series, recognizing it as a geometric series, identifying it precisely, so identifying the A and the R, the initial term and the common ratio, and then applying the result in the right way. Let's look at another example. Does the series sum of AM, where AM is, let's say it's 2 to the m minus 1 over 2 to the m, does this converge? Does this converge or diverge? Well, what is A to the AM? Maybe consider that a different way. We can rewrite AM as, see, really it's 2 to the m over 2 to the m minus 1 over 2 to the m. So you split apart the fraction and you see it's 1 minus 1 over 2 to the m. So it's certainly not a geometric series. You don't obtain AM by multiplying AM minus 1 by something. But what other feature can we observe here? I mean, the 1 is just a fixed constant. The 1 over 2 to the m, as m gets larger, 1 over 2 to the m gets smaller and smaller. So it goes a half, a quarter, an eighth, a 16th, whatever. Yeah. So this bit here, the bit you're subtracting from 1 is getting smaller and smaller and converging to 0. So we notice that AM is converging to 1 as m goes to infinity. So this series is an accumulation of steps, but the step sizes, they're actually getting bigger each time. They're getting bigger each time, and they're approaching the upper limit of step size 1. So it's like you setting off on a journey, taking small steps initially, but gradually your steps lengthen until they're pretty damn close to stepping 1 meter each time. You're never exactly stepping 1 meter, but you're getting very, very close to stepping 1 meter each time. You're going to do that infinitely often. So obviously you're going to travel very far. You're going to travel as far as you want if you wait around long enough. But more specifically, we see that it violates the general term test. So you see this first version of it. Here we have an AM where the limit is non-zero. The limit of the step size is non-zero, so we draw the conclusion that the series diverges. Okay? It's going to grow without any upper bound. So we can say that the sum of AM, m equals 1 to infinity, we can say that this diverges by the general term test. Okay, so it's a matter of when you're presented with a series, examining it, being able to recognize that one of these tests is applicable to it. Okay, so specifically here, this general term test. That's because it's the series terms are not getting smaller and smaller. They're getting larger and larger, in fact. Okay, let's look at a third example. This third example, it doesn't fit into either of these convergence tests we're talking about, but it does show up, again, the way we work with the partial sums. So we'll consider this series. You're summing up this quantity. 1 over n times n plus 1. So what does this look like? It looks like when n is 1, you've got 1 over, you've got a half. When n is 2, it's 2 times 3, so it's a sixth. When n is 3, it's 3 times 4, so it's a 12th, and so on. So you're adding up all those fractions that follow that pattern. Now, it doesn't violate the general term test. The terms you're adding up are getting smaller and smaller. So it potentially converges. Of course, that's not enough to guarantee that it converges. Okay. So does this converge? Well, for this one, we exploit a different representation, a different representation of 1 over n times n plus 1, which is an example of what's called a partial fraction expansion. It's actually possible to express this as a combination of these two simpler fractions. And in general, these kind of things lead to linear combinations of the two simpler fractions. Now, in a later chapter, we'll explore in very precise detail how to find these partial fraction expansions in all cases. But with simple examples like this, you can normally just identify the correct values for the coefficients by kind of trial and error. And what's it going to be here? We're just going to take 1 minus. So it's just going to be, we're just going to have a minus sign. So it's going to be this fraction minus this one. So if you follow the rules for adding those two fractions together, put it over the common denominator, n times n plus 1, you'll have n plus 1 minus n in the numerator, so you'll just get 1 in the numerator. Okay, so we exploit the fact that we can rewrite the term like this. And then we examine the partial sum. Examine the partial sum sk. Because remember that the sum of this infinite series is determined by the behavior of the sequence of partial sums. Okay, so we must look at the partial sum and look how it develops as k gets larger. Well, the partial sum, so it's the sum from n equals 1 to k of this 1 over n plus 1, but now we're going to use this form of it. So it's the sum from n equals 1 to k of the difference now between 1 minus n and 1 over n plus 1. Now to see what's going on here, it can help to write a few of these out. So the first term when n equals 1 is 1 minus a half. The second term is a half minus a third. That's when n is 2, you get these two. When n is 3, you get a third minus a quarter. When n is 4, you get a quarter minus a fifth, and so on. You get a load of these, and of course well, let's write down the last two. When n is k minus 1, you get 1 over k minus 1 minus 1 over k. And finally, when n takes its final value of k in the partial sum, we obtain 1 over k minus 1 over k plus 1. So that's what the partial sum looks like. But of course, you can see this isn't as complicated as it looks, because you've got minus a half, minus a third. So you get loads of cancellation here. So minus a half goes with plus a half, minus a third goes with plus a third, etc. This minus a fifth will cancel with the plus a fifth, which comes after it. This plus 1 over k minus 1, that cancels with the minus 1 over k minus 1, which comes before it. The minus k cancels with the plus 1 over k. So everything cancels. It's quite reminiscent of the geometric series thing we looked at, everything cancels except for the first and the last bit. So the partial sum is just 1 minus 1 over k plus 1. Now, how does that behave as k goes to infinity? Well, the 1 is just there all the time. But as k gets larger and larger, this fraction 1 over k plus 1 gets smaller and smaller and converges to 0. So it has the limit 0. So we see that the limit as k goes to infinity of sk, it's the limit as k goes to infinity of this. Well, that's just equal to 1. i.e., the limit of the sequence of partial sums, well, that's exactly the sum of the infinite series of the thing we looked at originally. We now see that that's equal to 1. So a half plus a sixth plus a 12th plus 20th was the next one. Adding up all those fractions gives you 1. Now, what was going on there has this kind of cancelling that you see in the partial sum. That's kind of given a name. We call this the telescoping partial sum. You know, those collapsible telescopes like the pirates would have, you know, fits in your pocket and you take it out and you stretch it out, and then you can look into the distance. So that kind of thing where you have this cylindrical object which folds down. That's reminiscent of what the partial sum is doing. So initially when you write it out, the partial sum looks really long, but it collapses down because all the intermediate stuff cancels out. You're just left with the stuff at the beginning and the end. So just the word we use to describe that behavior is the telescoping of the partial sum. So the partial sum telescopes down to something very manageable and something that you can understand the behavior of, okay? As opposed to trying to understand the behavior of a big long expression with a dot, dot, dot in the middle of it. It's very hard to give a precise evaluation of that. But when it just shrinks down to just the difference between two things, well, we can analyze that much easier. Okay, so that brings us up to that point where we've looked at all these, we've looked at those convergence tests. Now there's some more important convergence tests to come. The standard comparison test, ratio test. We'll deal with those next week. But in terms of exercises to be working on at the moment, I mean, I think you should be able to see your way up to question 6 there on page 19. So everything from 1 up to question 6, I think we should be able to get to grips with what we've done so far. Okay, now see you all next week.